Hello, everybody, and welcome to Mr. Saucedo's YouTube videos. Today, we're going to be going over Chapter 11 in Zumdahl, the 7th edition. We're going over properties of solutions. Some of this you already know. So, Section 11.1 is about solution composition. And so, this isn't necessarily on the AP exam, but I always like to introduce what a solution is, because most of the time people assume that the solvent is going to be a liquid and the solute is going to be a solid, and that when you mix them together, you're going to remain with mostly liquid, and that would be like seawater or sugar solution or something like that. But in reality, you can have two gases, a gas solute and a gas solvent. You can have two liquids, a liquid solute and a liquid solvent. You can have two solids. There are plenty of varieties of different types of solutions out there. Most of the time, the ones that we're going to be looking at are where we have liquid solvent and solid solute, or liquid solvent and gaseous solute. So like carbonated water, or like I said, seawater or sugar solution. So here's the trick, since we're dealing with AP chemistry for these videos. There are 4 different solution composition formulas. But because it's AP Chem, we only have to actually focus on 2 of those. We have to focus on molarity, which is abbreviated as capital M, and mole fraction, which is abbreviated with this kind of Greek letter called chi, but you could just use an X. And these are the only 2 that actually show up. Weight percent or mass percent of solution and molality do not appear on the AP exam anymore, so don't worry about any of that stuff. So let's talk about molarity. What is it? Molarity, like I said, is abbreviated capital M, and it's equal to the moles of solute divided by the liters of solution. So I know I didn't define them earlier, but a solute is what you have less of. The solvent is what you have more of. So you can think of it as the solvent is actually doing the dissolving. The solute is being dissolved. And when you mix a solute and a solvent together, you get a solution. Okay? And molarity is a great way of measuring how concentrated something is. So we have a very dilute solution, or we have a very concentrated solution. So this is, I believe, I think it's cherry Coke syrup, diluted with a lot of carbonated water and then not so much carbonated water. And so you can see that there's a difference between both, and there's a difference in the molarity. This is going to have a higher molarity. This is going to have a lower molarity. And I always like to use a PhET simulation to kind of introduce this. And so we have copper 2 sulfate, and you can see I have a number of moles here that I can shift around, and a number of liters that I can change here also. So you can see that as I remove solution volume, I'm getting something that's more concentrated. As I increase the amount of solute, I'm getting something that's more concentrated. And so if you want to make something more dilute, you either have to remove solute, or you have to add more solution. So add more liquid, in this case, to our little beaker. And so the nice thing is that if you take the number of moles and you take your solution in liters, you get the molarity of your solution. So you can see that. The cool thing about the PhET simulation is that in some cases there is actually a maximum molarity, and that would mean that if you add more solute than that number, you end up getting a saturated solution where you have solid crystals of it coming out at the bottom. And that is also something that you could calculate. You could see, like, right when you get to 1.400 moles per liter, anything you add above that, you start to get solid coming out in your solution. So if you were to take this number here and divide by this number here to get molarity, you would not get 1.400. So on the AP exam, you can assume that we're not talking about anything that would start to become saturated. All right, so now let's take a look at a couple of practice problems. Let's say I have 1 mole of sugar in 125 milliliters of solution. What would be the molarity of that solution? Nice and easy. 1 mole divided by, and remember this has to be in liters, and so I have to divide 125 milliliters by 1,000 in order to convert that, and so I get about 8.00 moles per liter. So I have a 8.00 molar solution of sugar. What if I have a 10.0 molar sugar solution? What volume of this solution do you need to have 2 moles of sugar? Again, not very difficult, right? I can take my 2.00 moles and divide by 10.0 moles per liter. And when I do that, what I get is 0.200 liters. So I would have, like it says here, 0.200 liters of that solution. Next up, consider we have separate solutions. So we have sodium hydroxide and we have another solution that is potassium chloride. We're dissolving 100 grams of each one of these in 250 milliliters of solution. What would be the concentrations of either one of these? So let's find the concentration of sodium hydroxide first. So I need to use my periodic table to find what the molar mass of sodium hydroxide is. And so what I get is about 40. So 100 grams divided by 40, that's going to give me the mole part of my fraction. I have 250 divided by 1,000. That's going to give me my liter part of my fraction. When I divide them, I get 10.0, a 10.0 molar solution of sodium hydroxide. Now take a guess. Do you think that the molarity of KCl with 100 grams of that is going to be greater or less than 10.0 moles per liter of sodium hydroxide? Answer, it weighs more. So potassium chloride weighs more than sodium hydroxide does. Its molar mass is 74.55. So when I end up doing the math for that, I get a molarity that is less because it is heavier. So 100 grams of KCl is going to basically, let's just say, take up more space than sodium hydroxide would. You can squeeze more sodium hydroxide into 100 grams than you can potassium chloride. All right, mole fraction. So mole fraction is equal to, I'm just going to say X instead of chi. So X sub A is what we're looking at here. That's going to be equal to moles of A divided by the total moles of solution. And you can repeat that for any mole fraction. So let's say we have, 3 things that have been dissolved. You could have a mole fraction of A, a mole fraction of B, and a mole fraction of C. Now, the trick to that is that when you add all of your mole fractions together, they have to add up to 1 because you can't have more than 100% of something in a solution. So here we have a solution of phosphoric acid that was made by dissolving 8 grams of phosphoric acid in 100 milliliters of water. Let's calculate the mole fraction of our phosphoric acid. And we are assuming that water, has a density of 1 and that we're not really worried about density here. Okay, how would we do that? Well, I have 8 grams of phosphoric acid. I would need to convert that to moles. So the molar mass of phosphoric acid is 97.994 grams. So I get this answer for the number of moles. Now remember, it's asking for the mole fraction though. So I need to know the mole fraction, so I need to calculate the mole fraction. I only have right now X sub A. I don't have the total number of moles. So we also have 100 milliliters of water. Again, we're assuming that the molarity, we're assuming that the density is still 1 gram per milliliter. So when I do my math here and I divide by my molar mass of water, I end up getting 5.55 moles of water. Now that kind of makes sense, right? If you're making a solution, you're going to have more water in it than you are your solute. So now what do I need to do? Well, I have everything I need. So to find X or X sub A or X sub phosphoric acid or whatever you want to call it, I would take my, moles of phosphoric acid and divide by the total number of moles, which is the moles of phosphoric acid plus the moles of water. And this is the fraction that I would get. So literally 0.0145. This is almost entirely water and very little phosphoric acid. The closer you get to 1 for your fraction here, of whatever you're looking at, the more of it there is. So I obviously have almost no phosphoric acid in the solution. All right. What about the formation of a liquid solution? How do you actually get and form a solution? So I always thought this was super interesting, right? So think about it. If I mix 2 things together and they dissolve in each other, what's happening? And so the first thing that you have to recognize is that you have to separate the solute into its individual components. So if you have solute that is solid, you have to expand and move the solute apart from itself in order for a solution to form. You also have to overcome any intermolecular forces in your solvent, because normally solvents are going to be things like water, and they have a lot of intermolecular forces. They have hydrogen bonding, dipole-dipole, London dispersion forces, right? All of those things are going on. And so you need to make room for solute, right? The solvent itself, if it's not a very forgiving solvent, it's not going to expand very much. And so you're not going to be able to dissolve very much solute as a result of not being able to overcome those intermolecular forces. And then last but not least, you have to allow time, right? We have to allow the solute and solvent to interact in order to form the solution. And there are ways we can speed that up, but it does take time in order for, your solute and solvent to evenly spread out. So what are our steps if we're looking at the energy here? And I think this is, again, pretty cool, right? So we have our solute. In this case, it is a solid. It's going to take a particular amount of energy to expand it. Our solvent, same thing. It's going to take a particular amount of energy to expand our solvent. And then when you mix them together, there's going to be a amount of energy that either is going to be absorbed or released in order to mix them thoroughly. And so steps 1 and 2, the expansion of the solvent and the expansion of the solute, require energy. It is going to take energy to separate the intermolecular forces in water in order to allow some solute to go inside, right? Now, step 3 usually will release energy, which is why most of the time when you mix something together in water or in any solvent, you normally end up getting a warming effect. Now, that isn't entirely true. Sometimes you do get, an absorption effect. And that, again, is something that is totally okay. It's just usually it releases energy. And so steps 1 and 2 are definitely endothermic because they require energy. Step 3, though, is often exothermic. Like it says, it releases energy. So why is that important to us? Well, enthalpy change is associated with the following. So you can think of the overall enthalpy of a solution, forming a solution, as being what we just said, the enthalpy of separating your solute plus the enthalpy of separating your solvent plus mixing them together, the energy required or released by mixing them together. And so, like it says, it may be positive or it may be negative. Positive signs mean that, again, energy is absorbed. Negative signs mean energy is released, just like any enthalpy question. So here are our two possibilities. Notice that in both cases, step 1 and 2 requires an input of energy, but depending how great the output of energy is, that's going to determine whether or not we have something that is exothermic, where we're releasing heat in this situation on the left, or where we have a deficit, and so we have a net absorption of heat, and so that would be an endothermic solution on that side. And so this is kind of cool. You can actually explain why water and oil don't mix based on enthalpy instead of just what you're used to saying, which is like dissolves like. And so let's take a look or think about the enthalpy of separating our hydrocarbons, of separating our water, and then of mixing them together. So I don't want to have to read this whole thing, but I'll explain it to you logically, right? So the amount of intermolecular forces in something like oil is going to be a pretty weak intermolecular force, right? It's London dispersion forces, but that depends on how big our molecules are. And oil molecules tend to be very, very large, right? The larger the oil molecule, like a triglyceride or something, the more energy it's going to take to separate those London dispersion forces from each other. So even though they're weaker than water, water's forces of hydrogen bonding, still, you can have a fairly or relatively large delta H1 for that, okay? Delta H3, I know we skipped H2, but we'll get back to that. Delta H3 is going to be pretty small because polar substances and nonpolar substances don't mix, right? Just generally speaking, they don't mix. So by putting them together, there's going to be very little interaction. So delta H3 is going to be tiny. Delta H2, though, is also going to be very large and very positive because it's going to take a lot of energy to overcome the hydrogen bonding forces in water molecules. And so because of that, our delta H of solution is going to be very positive and very large. And as a result of that, you're going to end up with something that really doesn't want to mix. And so here is kind of like a basic chart of that, right? If you have a delta H that's large and a delta H2 that's large, and then you have a very large delta H3 as a result, which means, it's negative, that means that you're going to have a very small delta H of solution, which means your solution is going to form. And that is typical of two polar substances being mixed together. Let's skip to nonpolar and nonpolar. Okay, typically, right, we would have H1 would be small, okay, because again, nonpolar solutes and solvents would tend to have very weak forces, right? And they would tend to be probably smaller molecules, something like methane, or even like, carbon tetrachloride, something like that, right? And so you normally get solutions forming from that too, from nonpolar substances mixing together. Now, if you have nonpolar and polar, though, in either conformation, whether it's solute or solvent, you end up with a mixture of things. And as a result of that, you end up with a very large delta H of solution, which means that no solution is going to form. Now, do you really need to know all of the details of this? Probably not. Okay, probably not. So in general, just keep in mind that there is an element of probability when we're talking about this, right? So you can increase the probability that these states will mix. You can do that in many ways, right? We can maybe apply heat or maybe cool it off, depending on whether it's going to be an exothermic process or an endothermic process. So there are things that we can do in order to kind of force polar and nonpolar things to do things that maybe they wouldn't normally want to do. But generally speaking, large amounts of energy are going to equal no reaction occurring. And when I say reaction, I guess I probably shouldn't say reaction. That's going to mean no solution forms, because it's not technically a chemical reaction we're talking about here. But again, overall, generally thinking that like dissolves like is totally fine. But keep in mind that you don't want to say like dissolves like on your AP exam. You want to use, let's say, a little bit more scientific language. So let's talk about structural effects. Let's talk about polarity and pressure, etc. So polarity, we kind of just talked about that. Okay, we'll talk a little bit more about it in a second, but polarity, we already kind of touched on that about polar versus nonpolar. Pressure effects, that's Henry's law. So Henry's law states that if you're dissolving a gas normally in a solution, if you increase the pressure, you're going to end up with more gas dissolving in, which makes sense, right? If I have CO2 and water, some of the CO2 is going to dissolve in the water no matter what. But if I double the pressure of it, I'm going to end up forcing more carbon dioxide into the water because now I've added more pressure to it. So there's going to be more contact between the carbon dioxide and my meniscus of my solvent. Same thing here. If I double it again, you can see there's going to be even more. Temperature does affect this also. And so for solids, generally speaking, but not always, increasing the temperature is going to add enough energy to separate those solvent intermolecular forces and to separate the solute particles in order to get them to, mix a little bit better than they would normally. And so you can see that as you increase the temperature, generally speaking, you end up dissolving more of, an ionic solid. All right, let's talk about that polarity stuff, though. So we do have hydrophobic substances, which are nonpolar. And so how can you tell if something's hydrophobic? Well, stay on the lookout for long chains with lots of carbon and hydrogens in them. Hydrophilic, water-loving substances, those are polar substances. What are you looking for? You're looking for things with nitrogen, oxygen, and fluorine in them. They have lone pairs of electrons. And so here's an example of something that contains nonpolar portions and polar portions. So we have a hydrophobic part of this molecule and a hydrophilic part. So you can see the carbon and hydrogens are all over here. So this little chain on this side is going to be very, very hydrophobic because we have lots of carbons and hydrogens. This side, though, we have a carbon with a double bond of oxygen. We have an oxygen with a minus charge. We have an sodium with a plus charge. So we've got over here a very polar area here. And so that is going to be hydrophilic. And in case you're wondering, this is an example of a soap molecule. So the reason why soap works so well is because the non-polar substance is going to stick to grease and oil, whereas the polar part of your molecule is going to stick to the water molecules. And so you have basically the perfect substance to deal with both non-polar hydrophobic things that are grease and grime and dirt, and hydrophilic stuff, which is what we're going to be using to wash it away, water. All right, what about pressure effects? Like we said, it's Henry's law really that we're looking at. Now, keep in mind, though, that Henry's law really doesn't affect the solubility of solids or liquids. We're really only talking about the solubility of gases. So Henry's law is this. It's C equals Kp. C is the concentration of your dissolved gas, and that would be measured again in molarity. K is your constant. P is the partial pressure of the gas solute above the solution. So you can kind of think of that as like in the previous slide's picture, or actually it wasn't the previous, it's 2 slides before. You saw all that carbon dioxide that was in the air that was being forced on. That would be the partial pressure of the gas solute above our little solution barrier, above our meniscus. And so the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above the solution. If you increase the pressure of the gas above the solution, you will dissolve more gas. Like it is a given fact in that situation. And so again, you can think of it like this. This is our liquid here. You can barely see it. It's probably not going to show up too well on screen here, but you can see that as you apply more pressure, you're basically forcing the gas molecules that are bouncing around to get stuck in the solution. So what about temperature effects? Well, again, solubility for most solids increases with temperature. There are some that decrease though, but just keep in mind that you will not really be asked to predict, is this substance going to increase or decrease in solubility, depending on whether you increase or decrease the temperature. That's something that you just kind of realize when you're actually doing the chemistry in a lab. And so memorizing those or anything would be just pointless. Keep in mind, though, that we're talking about solids, right? When you have a solid, you're going to, increase the temperature of the solution. You're probably going to dissolve more. On the other hand, if we're talking about a gas, so like Henry's law here, we're talking about a gas, the more you increase the temperature, the greater the likelihood that the gas actually disappears and goes into the atmosphere again. So you can see here, we have the solubility of several ionic solids and sugar. But take a look, right? It's pretty dramatic for sugar. And then look, we have some anomalies here. We have, sodium sulfate, for example, which actually gets worse as you heat it up. It doesn't dissolve as much, which is unusual. But notice for gases, it's the exact opposite. Obviously, as you heat up a solution that has gas in it, you're going to lose that gas. And so an aqueous solution, okay, so now we're on 11.4 vapor pressure of solutions. So keep in mind, right, that it takes more energy to remove something from an aqueous solution, because you can probably picture this a little bit, right? If we have pure water, evaporation is going to occur naturally anyway. If we have a solution, evaporation is going to occur, but not as much evaporation is going to occur. If you have an amount of water, an amount of salt water, and you want to see, hey, which one is going to disappear first and evaporate first, it is almost always going to be the pure substance, because there aren't other particles in here that are going to get in the way of you being able to evaporate. Whereas here you can see we've got all of these little tiny, other circles that are representing other ions here. And so to get enough energy to, move this water molecule and to let it escape is going to be a lot more difficult because of that. And so, like it says here, we have a closed environment. The water is going to evaporate and actually probably start to condense on either side of the glass, and you're probably going to get a lot of it condensing and going into your aqueous solution as a result. Now, the vapor pressure of solutions, non-volatile solute is going to lower the vapor pressure of your solvent, and that is a law called Raoult's law. And so Raoult's law involves, you guessed it, mole fractions. Our observed vapor pressure of our solution, that's right there. We have our mole fraction of our solvent itself, and then we have the vapor pressure of the pure solvent. So again, it's going to be some fraction lower than it would be because we have stuff, dissolved in our solution. So in its pure form, the vapor pressure would be just something you could look up in a book or online. But we have to look at our solution. Okay, how much of this is actually in our solution? So keep in mind that if we had none of our solvent, we would have a mole fraction of 0. If we only had our solvent, we would have a mole fraction of 1. So I'm going to actually go back, which is probably not a great idea, but notice that if this were 1, then the observed vapor pressure and the vapor pressure of your pure solvent would be equal to each other. And that should make sense, right? Because it's pure. But If we're talking about a solution, solutions always have stuff floating around in them. It's a solute plus a solvent. So you're always going to have some number that is going to be less than your vapor pressure of the pure solvent. All right, so that's enough Raoult's law. Let's look at section 11.6, which is about osmotic pressure. Osmosis, as you probably remember from bio, is the flow of solvent, in this case, normally water, right, into the solution or into a solution through a semi-permeable membrane. So there is a formula for this. We have pi, that's capital pi, by the way, equals m times r times t. Some of these should look familiar to you, but pi is osmotic pressure, and that's measured in atmospheres. Capital M is molarity, so the molarity of our solution. Capital R is our gas law constant, and that is 0.0821. And then T is our temperature, and yes, that has to be measured in Kelvin. So here is our example. We have pure solvent, we have a semi-permeable membrane, and we have our solution. So what's going to happen, because there are less, or I guess I should say fewer, because it's countable. I'm not an English major, so I don't really know. You can see that we have fewer water molecules on the right side of this semi-permeable membrane. So automatically, water is going to be able to move and go across. Now, because this is a semi-permeable membrane, that means only water is allowed to go. So you can see that, well, obviously we have less of this solute, but the solute can't get through the semi-permeable membrane. So now what you can see is water molecules start to move over until they are equal on both sides, and then we have an equilibrium that's established between both sides of our little pressure gradient here. And so pi equals m times r times t. Here's kind of the last test, if you will, of how to use osmotic pressure. So let's say I have 33.4 milligrams of a compound dissolved in 10 milliliters of water at 25 degrees. The solution has an osmotic pressure of 558 torr. Let's figure out what the molar mass of this mysterious compound is. So let's go through this. The first thing we need to get our pressure in a unit that actually is going to make sense for our equation. So I need to convert from torr to atmospheres by dividing by 760. Now I have my atmospheres equals m, my molar mass, which I don't know, times our gas law constant here. And then, yes, I converted 25 degrees Celsius to Kelvin. So now what do? Well, I know for a fact that when I figure out and solve for molarity, I get 0.030 moles per liter. Now, what other information do I have? Well, you can probably tell, right? I have gram information here. I have liter information here. What do I need in order to find the molar mass? Grams per mole. So I could take my 0.0334 grams, which, yes, I converted milligrams to grams, divide by 0.01 liters, since that would be my solution's volume, and I would get 3.34 grams per liter. Now take a look. I have moles per liter. I have grams per liter. What can I do? I can divide them by each other. 3.34 grams divided by 0.030 moles, and yes, the liters cancel, and I end up getting a molar mass of about 111 grams per mole. So that would be the molar mass of whatever substance was dissolved in this little osmotic pressure chamber. And that takes us to the end of Unit 11. So if you have any questions, let me know. But otherwise, thank you very much for watching, and make sure you like and subscribe.